So I am actually deeply honored, I'm going to move that Professor Serge Haroche, Nobel laureate 2012, has agreed to give the introductory presentation of our workshop. I was your student 30 years ago, and you taught me atomic physics and cavity quantum electrodynamics, and I must say that it has been a guideline all along my career. So I'm very grateful to have the chance to have you here today. Thank you for that. Professor Serge Haroche got the Nobel Prize in 2012 for the manipulation of single quantum system, in particular photon state controlled by single Rydberg atoms. He and his team showed how this system coupled to superconducting cavities containing few photons are ideal system for testing fundamental quantum laws and demonstrating logic operation that hold promises for the quantum technologies that we discussed today. Professor Serge Haroche was a professor here he's a professor here at Collège de France. He was even an administrator of the Collège de France, but he also conducted his research at CNRS. He was a professor at École Polytechnique, but he also at University Paris 6, but also in many places worldwide, in the US at Yale University, and a visiting professor in Stanford, Harvard, MIT, and the Federal University of Rio de Janeiro. So this is my great pleasure to welcome you here today. This, you will see, the talk is at the frontier between atoms and photons. As we said, these two systems, the two fundamental systems that we introduced for these lectures are really the core of these quantum technologies, where both atoms and light play the central role. So please welcome Professor Serge Haroche with me.
Okay, thank you, Pascal, for this very nice introduction. I am very pleased to be here and to attend this colloquium, which will be very interesting as a review of new light-based technologies. I apologize to have to speak seated because I have a bad knee, which makes it difficult for me to stand for a long time. I want also to say that I will try to follow your advice to start by simple notions and to go to more complex problems later on during the talk. As is not a surprise to you, I will talk about Rydberg atoms, which have been the tools that I have been using with my group during my whole career. These atoms have played a very important role from the start of quantum physics and even before, as a model to describe atoms. It's for the description of Rydberg atoms by Bohr that Planck's constant was introduced for the first time in physics. Later on, when it has become possible to do experiments with these atoms, they have become also very important in cavity quantum electrodynamics to study the basic interaction of light with matter and to demonstrate in the lab quantum entanglement and the preparation of state superposition known as Schrödinger cats. And then during the last 20-25 years, there have been a renewed interest in Rydberg atoms as systems which interact with each other at very large distances. So this gives the outline of my talk. I will start by discussing Rydberg atoms and the birth of quantum physics in the first part. Then I will talk about the use of circular Rydberg atom in cavity QED, making real the thought experiments of the early days of quantum physics. And in the last part, I will talk about Rydberg atoms for quantum simulation. What I want to say at the start that these atoms are very simple, and you don't need to know a lot of things about quantum science to understand them. You just need to know the early Bohr model, which is a quasi-classical model of the atom. And the paradox is that in spite of the fact that this atom is almost entirely classical, that it has very strong coupling to light, which exhibits quantum very important and very simple quantum features. Another reason for the interest in these atoms is, of course, that they have unusual orders of magnitude. So as an atomic physicist, when you work with Rydberg atoms, you have a thrilling feeling that you are like Gulliver in the world of giants. You have very unusual counterintuitive properties of the atom. And of course, the real reason I'm talking to you about this is because these are the atoms with which I've been working all the time. So I have always had fun to work with these atoms and to show that you can do interesting things with them. So let's start at the beginning. Of course, the Rydberg formula started even before the quantum age, at the end of the 19th century. This is the formula that Rydberg wrote. It explains the spectrum of hydrogen, explained with two numbers, which later on will be called quantum numbers, M1 and M2. And these numbers are used to classify the spectral line of hydrogen, which were known before. The Lyman series is defined by M1 equal 1, and the Balmer series with M1 equal 2. And you see here the Balmer series, red, green, blue, and violet line, which correspond successively to M1 equal 2, M2 equal 3, M2 equal 4, 5, and 6. And this formula was introducing the discreteness in physics, which was an idea which was completely different from classical physics, which described all quantities as being able to vary continuously. And the problem was to understand where does this discreteness comes from. The answer started to be given, of course, at the end of 19th, beginning of 20th century, first by the work of Planck and Einstein, who introduced the discreteness of the exchange of energy between light and matter. Planck explained the properties of spectrum of thermal radiation with this idea, and Einstein got a deeper explanation saying that light, which was of course a wave, was also made of discrete photons, discrete quanta, which later on were called photons. And of course the basic formula relates the energy of each photon to its frequency with Planck's constant h, which is a very small constant but still finite, and which has a dimension of an action, which will be very important in the following. It's an energy multiplied by a time, so it's an action, but it's also a momentum multiplied by a length, which is an angular momentum, and this property would be very important. At the same time, the discreteness of matter was also introduced by J.J. Thomson, who discovered the electron, and by Rutherford, who discovered the nuclei, giving the first model of the atom, a planetary model in which the electron is going around the nuclei. And this model was developed by Rutherford and by Jean Perrin. The next breakthrough was, of course, the Bohr hydrogen atom. Bohr considered the simplest possible planetary model in which the electron is going around the proton on a circle. This circular motion is, of course, defined by its angular momentum. So the angular momentum comes naturally into this model, and this Bohr assumed that this angular momentum was measured as an integer multiple of Planck's constant, which is, as I said, an angular momentum. So he wrote this formula, and for a reason which will appear clearer, it's not h, but h divided by 2 pi, which is called the reduced h bar, the reduced Planck's constant, which is important here. So this is one relationship between the velocity and the radius, but of course you have another relationship which is just Newton's law, stating that the Coulomb force, which is proportional to 1 over r squared, is equal to m, the energy of the electron, time its acceleration, v squared over r. So then you get two relationships, and it's just a middle school problem to solve and to find the radius of this orbit, which is scaled as n squared, and h bar squared or mc squared is a Bohr radius. So you see that as you increase n, the size of the atom increases proportional to the square of n, and you have the velocity, which scales as 1 over n, so the electron goes slower and slower as you get in higher orbits, and the energy, which is proportional to 1 over r, scales as 1 over n squared. The next hypothesis is just to say that when the atom emits or absorbs energy, it jumps from one orbit to the other, and the energy of the photon is just the energy difference between the two orbits, and so naturally the Rydberg law comes from that. And so this was a triumph of theory, the first introduction of Rydberg constant in atomic physics, and the Rydberg formula was recovered. In order to fit with the experimental data, you have to use h bar instead of h, but this will come naturally later on. This formula was very interesting, but it still had some problems, and it was not clear why you had to quantize the angular momentum, and it was not clear also to understand why the ground state orbit was stable. According to electromagnetic laws, it should radiate proportionally to the acceleration of the electron on the orbit. So Einstein called it in a letter to Lorentz, this is the worst of our physical puzzles. What is behind all this? An explanation was given a few years later with de Broglie work. De Broglie generalized the matter-wave duality, which was introduced by Einstein and Planck for light, to matter, saying that matter was also a combination of discrete and wave-like properties. And to do that, he made a kind of mixture between quantum physics and relativity. He started with the photon energy. The photon momentum is equal to h over lambda, according to that, and he assumed that this relationship, which is basically relativistic because the photon goes at the speed of light, could be used in non-relativistic physics to relate the momentum of the electron to its wavelengths. And if you use this formula, lambda is equal to h over mv, you find immediately that the Bohr quantization is just expressing the fact that along the circular orbit, there should be an integer number of de Broglie wavelengths. So it's a resonance condition of wave mechanics, which was a great contribution of de Broglie to that. This de Broglie matter wave justifies the Bohr angular momentum quantization rule with a 2 pi factor. And so Einstein loved this explanation, and he wrote to Langevin, your student has started to lift the veil hiding the quantum world in 1924, and Einstein was right, because a few months later, in January 1926, Schrödinger found the equation which describes the evolution of the Broglie wave. This work had been preceded by a few months by Heisenberg, who introduced another way of describing that by matrices, describing operators. So I don't want to enter into this early discussion, which was rather complex, but it was found that these two approaches were equivalent, and of course Bohr found that the square of Schrödinger equation was the probability to find the electron at a given point. I just show you here what are the consequences of all this for our problem. In the hydrogen ground state, the wave function extends in a very small region of space, about 1 angstrom. It corresponds to n equal 1, but to L angular momentum equal to 0. So there was a small mistake in the Bohr's approach. The smallest value of the angular momentum is 0, not 1, and the largest value for a given quantum number is n minus 1 and not n. But of course, this makes a little difference when n is large. And you see at the same scale, the wave function corresponding to circular Rydberg atom with L equal to 49, n equal to 50. So the wave function orbital is a kind of torus around the nucleus at a distance which is very large, thousands of times larger, so which will give the interesting properties of these Rydberg atoms. To understand these exaggerated properties, you can use Bohr's law and the correspondence principle, which says that at very large numbers, quantum physics and classical physics should meet. And all these orders of magnitude can be recovered by simple back-of-the-envelope calculation. For example, the electron period is just the circumference divided by the velocity, and the scaling is n cubed. It's n squared divided by 1 over n, so it's n cubed. It says that the period of the electron, which gives the frequency at which the resonance between light and matter will occur, scales as n-3. So instead of interacting with optical photons, Rydberg atoms interact with microwaves. They interact very strongly because the electric dipole is large. It's a kind of large antenna scaling as n squared. So it immediately gives the very strong resonant coupling to microwaves. Another classical deduction: what is the spontaneous emission lifetime on a circular state? Classically, the radiation rate of an electron is proportional to the square of its acceleration. So the acceleration is v squared over r. It scales as n-4. When you square it, you find n-8. And this is the rate at which photons are emitted. And since the energy of each photon scales as n-3, the rate at which the emission occurs scales as n-5, which means that the relative lifetime is proportional to the fifth power of n. It's very long. For circular Rydberg state, the lifetime falls in the 100 of millisecond range. And this explains the advantage of circular state over non-circular Rydberg states. If you take an elliptical state, its acceleration will become much larger at the perihelion when the electron gets closer to the nucleus, and so the lifetime is much shorter. So if you need to have very long lifetime system, which are nevertheless very strongly coupled to radiation, the ideal system is a circular atom. Last properties: if you have two Rydberg atoms at a close distance from each other, they interact through the dipole-dipole interaction, which scales as n to the fourth power, which makes it very important at distances of several micrometers. Scales at n to the fourth divided by r cubed. In the case when the interaction is active at second order, you get the van der Waals interaction, which scales as n to the 11, the square of n fourths, divided by the energy distance between nearby neighbors, which makes n to the 8 times n to the third, and it gives you this huge enhancement, which will be, of course, an essential feature when you will talk about Rydberg atoms interacting with each other. So you have very strong atom-atom interaction at tenths of micrometer distances. Of course, these atoms were very difficult to observe in the lab for almost 50 years because they are very fragile. And the first places where they were found is the interstellar space. You have radio telescopes which detected them in the 1960s, mostly by Russian telescopes in Crimea and in the Soviet Union. You see here the microwave lines corresponding to the capture of free electrons, which were produced by photodissociation of atoms due to the UV radiation of the stars, and which recombined with free electrons on circular orbits. And you saw the radiation of these atoms decaying from one circular orbit to the next. All the Rydberg states of different elements have very close frequencies because they're all hydrogenic except for the small reduced mass difference, small isotopic shifts. So you see here lines corresponding from Rydberg emission of hydrogen, helium, carbon, and so on. And I think the record is a line in carbon, an emission from 732 to 731 Rydberg level, occurring in the range of a few gigahertz, the radius of the corresponding atom being 53 micrometer, which is, of course, the width of a hair, so it's a rather macroscopic system. The first occurrence of these atoms in physics started in the 1970s when lasers were able to excite selectively atoms very close to the ionization limit. So in the first experiments, these levels were reached by stepwise excitation, first in alkalis, this is the case of rubidium, first the resonance line from 5s to 5p, and then with a second or a third step very close to the ionization limit. Since each photon carries 1 unit of angular momentum, in this way you get to low angular momentum state called SPDF for L equals 0, 1, 2, 3. These are classically very elliptical orbits with rather limited lifetimes. But then when you get close to the ionization limit, you have transition between states of increasing angular momentum, which fall in the microwave and in the radio frequency domain. So by exploring these states, having the atom absorb microwave and circularly polarized photons, you eventually get to the circular state, which is a state of maximum angular momentum. This physics was developed in the 70s, and the circular state preparation was pioneered by Daniel Kleppner at MIT. What he did was first to excite the atoms in a low angular momentum state with lasers, then apply an electric field, and it leaves the degeneracy of the state according to the Stark effect. And you see that you can classify the level by increasing value of the angular momentum. And so when the angular momentum increases, the number of states decreases until you reach at the tip of this lozenge state, non-degenerate states, which are the highest value of the angular momentum. And the way he did it was after the laser excitation to apply circularly polarized radio frequency photons, which allowed to go step by step toward the extreme state. In fact, it's not step by step. What he did was to sweep the frequency of the radio frequency field to cross the resonance in an adiabatic way, which brings continuously the atom to the circular state. So it was a very clever technique developed by Dan Kleppner. And I quote Dan here because he was really a pioneer of many fields in physics, including Bose-Einstein condensation, but he was a pioneer of Rydberg atom physics. And myself and my group had the privilege to work with him at the end of the 1970s on these problems. He just passed away about 1 year ago. He also demonstrated the selective detection of Rydberg atom by field ionization direction. If you think of the Rydberg atom, it's an electron in a circle with a nucleus in the center. If you apply an electric field, the proton and the electron are pulled in opposite direction. At the beginning, it just changes slightly the frequency of the electron motion, which is a way to tune the Rydberg electron in and out of resonance of, for example, of a cavity, and we will use that. And if you go on increasing the electric field, the shape of the system becomes like an umbrella with the electron at the center. At some point, the system breaks, and this breaking occurs for different electric field values as n increases. And you see here on this figure what happens in a ramp of electric field. You excite successively when you increase the field, circular Rydberg state of decreasing n values. And so you can selectively ionize in a ramp of electric field, and it is a method which was widely used to detect these atoms. The method has limitation because it's not, it's a destructive method, which is not very useful for the talks I will describe in the last part, for the phenomena I will describe in the last part of the talk. And it's also not spatially selective. You excite the atoms wherever they are inside the condenser plate, which applies the electric field. Last description of Dan Kleppner's work. Once Dan Kleppner had prepared circular state, he demonstrated a very interesting effect, which is the inhibition of spontaneous emission. You have prepared circular atoms in a thermal beam. The atoms were crossing a zone in which two metallic plates were making a kind of waveguide, and the waveguide was beyond cutoff for the frequencies that the Rydberg states wanted to emit on the circular to circular transition. If the gap was smaller than half the wavelengths the electron would emit, it was beyond cutoff, and the Rydberg atom could not emit photons. So what happened is that the atom stayed in the excited state. If you increase the gap or more easily decrease the wavelengths of the photon by scanning the electric field so that the photon can be emitted inside the gap, you see a sharp increase at the when the Rydberg atom emerged, a sharp increase of the flux of Rydberg atoms, which is a demonstration of the inhibition effect. Of course, after this large maximum, the number of atoms drops down because the atoms can emit outside when they escape from the gap. But this signal was a very interesting experiment. And in Paris, at the same time, we did the opposite. We showed that the Rydberg atom crossing a cavity which was tuned to be exactly in resonance with the frequencies that the atom would like to emit, the spontaneous emission was not inhibited, but was enhanced. So at that time, we worked very closely with Dan at MIT. And you see here a picture which was taken at Les Houches, in the Les Houches school in 1982. I am with Dan, and we are discussing what we could do with the system. It was also a time when Herbert Walter in Germany was working on the micromaser, which was a device using the same principles, showing that you can get a maser operating with one Rydberg atom at a time, crossing a very high Q cavity. And in 1989, I wrote with Dan a kind of review article in Physics Today, in which the name cavity quantum electrodynamics was used, I think, for the first time. You see here a picture showing the Herbert Walter micromaser. So these were the early days of quantum physics, of quantum electrodynamics, in which the lifetime of the interaction time between the Rydberg atom and the microwave was still too short compared to too long. I mean, compared to the time it takes for the atom to go from one level to the other. So, by increasing the Q of the cavity, we were able to have this photon staying in the cavity long enough to be reabsorbed by the atom, which is a strong coupling regime of cavity QED. And this led me to a brief description of the experiments that we did in the years 1990 and the years 2000. So in our experiment, we have two different kind of setup. In the first setup, we had the Rydberg atom going horizontally at thermal velocity through a very high Q cavity. The lifetime of the cavity could be increased to 0.13 seconds by having the mirrors coated with superconducting niobium, and this meant that the photon could stay in the cavity for many, many atoms crossing it one by one and looking at the strong coupling of the atom with the cavity field. In a later version of the same experiment, we had the atom going vertically across the cavity, slow atoms which were crossing the cavity over a much longer time, and we could get this interaction going on for many, many interaction time. What we observed is called the Rabi oscillation. You can interpret it either as a kind of ping-pong game between the atom and the cavity field, the excited atom in the upper state emitting a photon into the cavity and then reabsorbing periodically the photon. Another way to view this, which is deeper, is to say that it's a quantum interference phenomenon. The two states, E0 and G1, are degenerate, but in the presence of coupling, the degeneracy is lifted, the symmetric superposition acquires a higher energy than the antisymmetric superposition. And so if you start with the atom E0, it is prepared in a superposition of the two energy states. And this superposition evolves at a rate which is equal to the frequency difference, omega. And so as a function of time, you get the system going into a superposition of E0 and G1, and this is called the Rabi vacuum oscillation. Of course, it can be extended to larger photon numbers. This oscillation having its frequency increasing as the square root of the number of photons minus 1 in the cavity. In this way, you entangle the field and the photon, the photon and the atom, and this entanglement leads to the possibility of building quantum gates in which the photon is the control and the field the target. So as soon as you get entanglement in a system, you can develop all these procedures of quantum information theory. So we did that. We also had two atoms crossing the cavity, one after the other, and then we were able to transform the atom field entanglement into an atom-atom entanglement and demonstrate gates in which the first atom is the control of the state in which the second atom will go. This happened in the mid-1990s, and in fact, we had started all this game without knowing what quantum information was about, and then we understood that we were doing quantum information without knowing it. The same thing happened with Dave Wineland in the United States, and we started so competing in a field which we ignored at all the importance of, and this has been going on for many years. We can also use these methods to detect photons without destroying them, quantum non-devolution measurements, and we did that by having the atoms interact non-resonantly with the cavity field. If the photon frequency and the atomic frequency are slightly different, the photons cannot be absorbed, but the presence of a photon in the cavity slightly shifts to second order the atomic resonance by a quantity which is proportional to omega squared, the Rabi frequency squared divided by the detuning. This means that you can observe this shift by doing a Ramsey interferometric experiment. You have the cavity sandwiched between two auxiliary cavities, R1 and R2, in which microwave pulses are applied. And so what you realize, in fact, is a kind of atomic clock. It's exactly the design of the cesium clock, in which cesium is replaced by the rubidium atoms. And this cesium clock is perturbed by the cavity field in such a way that the Ramsey fringes that you have usually in atomic clocks are shifted. And due to the huge coupling between the Rydberg atoms and the microwave, the shift can reach a value such that when the number of photons goes from 0 to 1, a fringe maximum is replaced by a fringe minimum. And so if you tune your system to be at a maximum of a fringe when you have 0 photon in the cavity, you are at the minimum of the fringe for 1 photon, which means that a single atom crossing the cavity, when it is detected, tells you whether you have 0 or 1 photon in the cavity, but without absorbing the photon. So it's a method which is completely different from the photoelectric effect, which destroys the photon as they are detected. And you see here the first signals that we obtained in 2006, where hundreds of atoms cross the cavity, signaling that the cavity is in its ground state. And when a photon pops in the cavity due to thermal fluctuations, you get a sudden change of the photon number, which stays equal to 1 for some time, and then goes back to 0. So it was the first time it was possible to observe quantum jumps of the field and to see that the photon could be detected without being destroyed, which was a way to store information in the cavity for some time. So this experiment, which allowed us to see the birth, life, and death of a photon, enabled us also to count larger photon numbers by having many atoms crossing the cavity and acquiring more and more information about the photon field. The last point I would like to stress with these experiments is the fact that it was possible to build superposition of quantum state of the field containing several photons. The idea is again to be off-resonant. This is the simplest way to explain that experiment. And the atom which crosses the cavity cannot be absorbed, but it acts as a kind of transparent medium, which during the time it is in the cavity shifts the frequency of the field, such that the phase accumulation of the field will depend upon the presence of the atom in one state or the other. So what we did was first to prepare a field containing a few photons, a field which has a well-defined phase, a coherent state, which can be represented as an arrow in the Fresnel plane. The length of the arrow gives the amplitude of the field, and the direction of the arrow gives the phase of the field. And having one atom prepared in a superposition of the two Rydberg state, so when the atom crosses the cavity, it is shifting the phase of the field in both directions at once, and you get an entanglement now between a field and a coherent field with two different phases and an atom. And this phase shift can reach the value pi, which means that you can have a field which has one phase or the opposite phase. If you detect at this point the atom, you collapse the field in one phase or the other. But the trick is to have, again, the Ramsey setup. The atom crosses the second cavity, so the information about the state of the field is erased. You don't know in which state the atom one was when it crossed the cavity, and when you finally detect the atoms, you leave the field in a superposition state with opposite phases. And the opposite phases is plus or minus, depending upon the state in which you detect the atom. So you get, in fact, what is called Schrödinger cat state of the field. And by having other atoms crossing the cavity after that, you can reproduce statistically by having many realizations of the system, measure what is called the Wigner function of this cat state, which is a phase space representation of the state. And you see here the kind of pictures that we obtain. The two peaks correspond, so to speak, to the live and dead cat, which contain a few photons. And you see in between positive and negative fringes of the Wigner function, which are a signature of the fact that this superposition is coherent. It's not a dead or a live cat. It's at the same time a dead and a live cat. They both coexist with a well-defined phase relationship between the two parts of the wave function. What we did next was to let this system evolve as a function of time and take snapshots for increasing times. And you see that after about 10 to 15 milliseconds, the fringes are erased, which means that the system is going from a quantum superposition into a statistical mixture. So this describes what is going on when you go from quantum to classical. A classical system is a system which is either dead or alive, and not the two at the same time. Of course, we still get the two peaks because this experiment is by definition a statistical measurement of many events. So 50% of the time you are in one peak or the other, and when you reconstruct the average, you get, of course, the two peaks, but you lose the fringes. So these were the experiments which showed this quantum to classical transition. I must say that this kind of experiment is now performed in circuit QED, in which Rydberg atoms are replaced by artificial atoms, which are much larger, superconducting junction physics. So all these processes occur faster, and these Schrödinger cats are used in many devices to try to develop error-correcting codes for the search for a quantum computer. I want to say that this is a kind of research which was recognized by the Nobel Prize. I must emphasize the role played by my colleague Jean-Michel Raymond and Michel Brun in this work, and also by the work of three people who were postdoc in our group and students and postdoc, and then became independent PIs, so Igor Dodsenko, Sébastien Glaise, and Clément Serrin. And we have had many other people coming here, and I'm glad to see some of them here, Alexia. And this was really a work over many decades, and I'm very grateful to all the students and postdocs who helped us doing that. And I just now have to go to the last part of the talk, which is the use of circular Rydberg atom for quantum simulation. So what I want to say at this stage is that the experiments that we did until the year 2000 were developed in a very small number of groups. Very few groups were working with Rydberg atoms, and even fewer with circular atoms. I think we were at the time the only one who worked with circular atoms. And now, 25 years later, I think there are hundreds of groups working in the field of quantum information using Rydberg atoms as competitors, candidates for developing quantum qubits for quantum information science. The idea is that Rydberg atoms are not only very strongly coupled to microwave, they are also very strongly coupled to each other. And this is for the same reason, because as you know, the coupling between atoms is due to the exchange of photons. So if they are very sensitive to microwaves, they are very sensitive to each other. You see here two Rydberg atoms, two circular Rydberg atoms, which are held at a very well-defined place in space. The coupling is just the dipole-dipole coupling, which has an isotropic part, which is a product of the dipoles, and an isotopic part, which includes the product of the projection of the dipole on the interatomic distance. This is a dipole-dipole coupling that you have also in magnetism, the same kind of coupling you have when two magnets are at a fixed distance from each other. And this is not a coincidence. It explains why this Rydberg atom system can be used as simulators for magnetic system in which the magnetic interaction is replaced by an electric one. So in this case, you have two different situations. A situation when this interaction acts to first order. For example, if you excite one Rydberg atom in the n circular state and the other one in the n-1, these two states are directly coupled to each other by the dipole interaction, and so the system flip-flops between the two states in which they just exchange their excitation, n-1 being coupled to n-1n. This coupling is very similar to the one I had before. Instead of coupling, I described before, instead of coupling an atom to a cavity, now you couple two atoms to each other. The coupling gives rise to a flip-flop, a kind of Rabi frequency occurring at a frequency proportional to n to the fourth over r cubed. And this Rabi oscillation is called, in this case, a Forster resonance. The second possible situation is a case when you don't have a direct coupling to the other state. For example, if you excite the two atoms in the same state, n, one atom will go up, the other down, but because of the anharmonicity of the energy spectrum, the final state does not have the same energy as the final one. So you have to look at the interaction to second order. This is what happens in ordinary matter when two atoms are in the ground state. This is called the van der Waals interaction, and it acts to second order, so it's an effect which scales as n to the 11th power over R6. And the two situations can be found very easily because you can tune, either you have automatically the same frequency, or if not, you can use the Stark effect to tune in resonance whatever you want. So the recipe to do this kind of experiments is to be able to excite the atoms to Rydberg states, of course, to keep them at a fixed distance in a lattice. For that, you use tweezers, which act as a gradient of a very strong non-resonant field, which keeps the atom at a well-defined position in space. You need to detect the atom selectively and hopefully non-destructively. You need to tune their interaction by applying electric or magnetic fields. And this will allow you to make quantum simulators of spin system. I don't dare to talk about a quantum computer because we are very, very far from that. And I will say a few words about the limitation at this point. So the phenomenon which led to all this fashion to work on these Rydberg atoms is a dipole blockade effect. So assume that you're able to have two atoms trapped in the ground state at a well-defined distance from each other by two tweezers, which you can obtain by just shining on a lens light beam at a small angle. What happens immediately is that you will not be able to excite the two atoms with the same laser light. If you excite one, you will have an energy shift which will prevent you to excite the other one because it will get out of resonance. So you can only excite one atom in the vicinity of another one. It's called the Rydberg dipole blockade effect. If you try to have a beam which overlaps the two atoms, which is very easy to do, then what happens is that you excite symmetrically. You get one excitation shared between the two atoms, but you cannot excite to the second level because of this blockade effect. So what happens naturally is that you prepare a delocalized excitation, which is an entangled state. It is either the first or the second atom which is excited, but it is simultaneous, and you get all the features of quantum information. As soon as you have entanglement, if you combine this with single atom manipulation, adding pulses, pi/2 pulses, which excite one or the other atom into a system, it's very easy into a Rydberg state. It is very easy to build quantum gates in which one of the atoms is the control and the other the target. And so this was the reason why this field started. Peter Zoller and Michel Lukin and Ignacio Cirac wrote in the year 2000, 2001 papers in which they described this, and this has given rise to the start of this physics. You see here a typical example of what Antoine Brouet in the Institut d'Optique in Palaiseau did, which is to do this experiment with a lattice of atoms, excite them with lasers, and in some condition you can have a situation in which one atom out of two is excited, so you can see it, and I will explain why, and between them you have dark spot, which means that the atom is not in the ground state, but in a Rydberg state, and this simulates antiferromagnetic materials, and so you can use this to simulate antiferromagnetic of different kind of, try to find different phases of magnetic materials and study many body condensed matter system, and it's also a system which is used for the research on quantum computers. So let's go in a little bit more details, and here I will focus on what is being done at the LKB lab here at Collège de France, and I want to state from the start that I am following very closely what the group is doing, but I am no longer participating directly in that. So what I will talk about is work done in the group, which is headed by Michel Brune now. And if you have any question at the end, any technical question, I hope that he will answer to this question. So this will a little bit alleviate the kind of uneasiness I have to talk about this in front of him. Okay, so the system that we are using is shown here. You start in rubidium atom, you start from the ground state, and you have a 2-photon excitation to the 52D state by pulse, which can be a pi pulse, which can excite all the atoms by half a Rabi oscillation into this state. Then you have a microwave, which brings you from the 52D to the 52F state. This is also unitary transformations. You can, in principle, send all the atoms into the 52F state. And then you have the Kleppner method to circularize this state by having it absorb in an adiabatic process circularly polarized radiofrequency photons in a small electric field, and you reach the 52C circular state. So this is one of the two qubit states that we are interested in. And then we are looking at what happens when this system absorbs 2 microwave photons to do a coherent transition between 52 and 54C. So in fact, in the excited state, we get we can prepare and manipulate a superposition of these two circular states, which can be described on a Bloch sphere. So the 54C state is the spin pointing up, 52 spin pointing down, and a superposition with equal amplitude along the equator of the sphere with a controllable phase. The problem is that this circular state is blind to light. It cannot emit photons. The only thing it can do is to emit or absorb microwave, and if you want to detect, one simple thing you can do is to do the opposite process, to bring the atom down with the same kind of coherent pulses, and once you are back in the ground state, apply a resonant laser exciting 5S to 5P, and then look at the fluorescence of the atom. So what you detect is the result of what happened after you have done all your manipulation back into the ground state, and of course this is destroying the states that you are interested in. So it's not an ideal method, but I will tell you how they can what they can do to avoid this problem. So I just recall very briefly here something which may have been discussed in earlier seminars of this course. And how do you prepare an optical lattice of tweezers? What you have to do is to, of course, to focus the light in a optical trap of cold atoms, and to have multiple tweezers. And each tweezer will attract one atom, no more than one, because if there is more than one, there is a light-assisted collision which will expel the atoms. So you have 0 or 1 atom left. And what you have to do is to be able to tailor the distribution of tweezers as you want. For that, the trick is to have the laser beam fall on a spatial light modulator, which modulates the phase of the light, so that when you focus this light, according to the Fourier transform operation that the lens does, you get a distribution of points, and you can find out the kind of phase modulation you need to do by an algorithm which tells you what kind of phase modulation will give you the adequate distribution of optical lattices. So this is in particular what Antoine Bohr is doing in Palaiseau. You see, when you start with that, you get a half-filled lattice, because half of the time the atom, there is an even number of atoms, and they get all expelled. And what you can do then is to use one movable tweezer to take atoms at the periphery of this distribution and bring them to fill the empty spots. And so you rearrange the system so that you fill all the spots. And this is what Bohr and the people in Harvard and all the people who now work with this kind of system do. And you get this kind of system. The problem, again, is now that the Rydberg atoms are not trapped in the system. They are trapped in the ground state, but as soon as you send them in the excited state, they are expelled from the trap. And so if you want to do experiment with the system, you have to go fast and to do all the manipulation in a time short compared to the expulsion time, which is of the order of a few microseconds. So the reason why the Rydberg states are expelled is the fact that the Rydberg electron is like a free electron, and what the light field is doing on it is just to shake it at the frequency of the light beam, and this shaking is giving it a kinetic energy which is positive. So instead of having a well, you have a kind of barrier, and as soon as the Rydberg atom is at the top of this barrier, it will roll away with a kinetic energy which increases. So in order to avoid that, and again this was pioneered first in the Antoine Bohr's group, is to replace these tweezers, which are obtained by having red detuned light acting on the atom, by blue detuned light, and by having a kind of wall of light, kind of optical bottle around the atom. And these are called bottle optical traps, bottle beam traps, Bob traps. And to obtain them, the only thing you have to do is just to change the phase distribution on the spatial light modulator to go from one configuration to the other. So the technique is, what we have to do is shown here. Now we have two spatial light modulators, one which is used to trap the ground state atom, and the other which is used to trap the Rydberg atoms. So double trap procedure with one SLM using for one kind of atom, the other for the other one. And you just shift from one kind of trap to the other according to the experiment you want to make. So I show you here what they did when they wanted to study atoms in circular state. You start by trapping the arranged ensemble of ground state atom with tweezers, so at the left of the slide. Then you switch off the tweezers and you excite low angular momentum state in Rydberg state. At that point, you switch on the bottle beam and you prepare the circular atoms in the Bob trap using first a microwave step, then a radio frequency sequence of absorption. Then you are in the red region in the bottle beam. You have hopefully an ensemble of atoms at a well-defined position. You let them interact for whatever you want to do with them. And then to detect, what you do is that you reverse the procedure. You start by de-excite the circular state, then you switch off the Bohr trap, you de-excite the Rydberg atom, and you come back to the ground state, and then you switch on the tweezers. If the atom comes back to the same state that it started from, you get fluorescence. If during the process in the middle he went to another state, when you come back, there will be nothing. So you get a signal or not, and this gives you a kind of single bit information about what happened to the atom, whether he stayed in 52C or went to 54C. So it's a state-selective detection, but the problem is that the system is destroyed and you have to start all over again. So first of all, I want to show you here with this slide how complex the whole thing is. You need a lot of lasers, a lot of SLMs, a lot of acoustic modulators, a lot of detectors, and so on. And I will just insist on the fact that you need many lasers. You need lasers for the mode trap. You need Gaussian tweezer you need lasers for the Gaussian and the Bob tweezers, and for the rearrangement tweezer. You need lasers, blue and infrared, to selectively excite the Rydberg state in a two-photon process. And you need a near-infrared laser for the optical pumping and fluorescence detection of the ground state. But whatever lab you visit in which this kind of experiment is being done, you have all the table full of optical equipment, which is much, much, much more complex than the kind of equipment we had at the beginning in cavity QED, and even simpler that we had in the 1970s when I was doing the kind of experiment we did with Dan Klepner, where we had only 1 or 2 lasers, 1 or 2 mirrors, and 1 photomultiplier. So it says a lot about all the skills that PhD students have to acquire now before they start doing this kind of experiment. So what can we do to avoid destroying the system? The trick that the group found was to use probe atoms which are prepared close to the Rydberg, the atom which will be carried into the Rydberg state. So the big red spots are target atoms in the Rydberg state of interest, and the small greenish yellow traps around are probe atoms, which we used through the dipole blockade to get information about the state of the quantum bits that we are using. So you see what happens here. In fact, if you want to say it in an imaged way, the Rydberg atoms are blind. They don't see light, but they can be helped by guide dogs, which are the other atoms. They provide information, and they allow us to manipulate and to observe the blind atoms. So how does it work? The principle is a dipole blockade. You see here the relevant energy level of the target, 52C and 54C, and you have a 2-photon microwave transition which couples them, and you see between 52 and 54 you have 53, which is not resonant because the anomalisticity of the energy scale, but which will be useful in the experiment. And the probe atom, which is close to the Rydberg atom, the atom in Rydberg state, has as relevant energy level 5s, which is the ground state, and 2 levels, 45s and 45p, which turn out to be resonant with the 44C to 53C transition. And in order to get this exactly resonant, they have to apply a small electric field which tunes this transition into resonance to get a Forster resonance, which is shown here, an exchange between 54C and 45S. So you see that if you take the spectroscopy of the probe atom, if you tune the 2-photon excitation, you have 2 different results depending upon whether the target atom is in 52C or 54C. If it is in 52C, you see a sharp resonance because 52C is not affected by the Forster resonance. But if you are in the 54C state, the Forster resonance splits the transition 54C, 53C in 2, and you need now to tune the transition below and above the frequency of. I don't know why it started to work alone. It emancipated itself and goes too fast. So I come back, and so you see what you have to do is to tune the probe in order to try to excite 45S and look at what happens, whether it will be excited or not. So you see what happens if you see the sequence of events that you apply. You start by preparing the probe in the F equal 2 ground state of rubidium. Then you apply a pi pulse, which try to excite 45S. Then you do your experiment, and then you apply another pi pulse, which try to bring you back to the ground state. And in between, what you do is that you probe the state by doing an optical pumping from F equal 2 to F equal 1 in the ground state. Or you could do a Raman two-photon process if you want it to be unitary, to go to F equal 2 to F equal 1. So what will happen? Suppose that the target is in 54C. Then you will not be able to excite the atom, and the transfer from F equal 2 will bring you to F equal 1. If, on the other hand, you are in the 52C state, then you will empty this state, and then the optical pumping or the Raman process will have no effect because there will be no atom left in the ground state. And when you come back, you will be in the F equal 2 state again. So you see now that you have transferred, and you can do it in a unitary way, the atom to the quantum state between 54C and 52C into a superposition of state F equal 1 and F equal 2. So it's quantum non-demolition. And of course, when you detect F equal 1, F equal 2 by fluorescence, you of course get one result or the other, but this is the definition of a quantum measurement. It is a quantum non-demolition measurement. I will just show you one example of what you can do. How can you now, how can you prepare a 5 minutes, 2 minutes? You can prepare a distribution of atoms initially in 52C and 54C. What you can do is to prepare all the atoms in 52C, and then you can block the transition from 52 to 54 by having probe atoms which shift the resonance of 54 out of resonance. So if you block this, and if you try to excite by microwave into 54C, you don't get any excitation. But if you want to selectively choose which atom you want to be able to excite in 54, you suppress the excitation of selected probe by using off-resonant lasers, which light shift 5S states specifically for some atoms. And this works. And when they do that, they can, for example, prepare one atom in 54 and another atom in 53. If you do that, you get now a system in which you can do this energy exchange between the two and excite a Forster resonance. Once you have excited the Forster resonance, you can transfer 53 back into 52 and measure the final state, and you see the Rabi oscillation. So this was just a demonstration of the fact that it's possible to do that. Now, since I see that this is finishing, I would just tell you that there is another way to do this kind of experiment. What we want to achieve is, of course, to have a microwave qubit, but at the same time be able to detect it at an optical transition. And another way to do it is what another group in our lab is doing. It is to excite Rydberg states in strontium atoms, in alkaline earth atoms. Then you have 2 electrons in the system. You can have one electron excited into Rydberg state, and the other electron being a valence electron that you can excite around the strontium core, which is sensitive to optical transitions. So I don't have time to describe the beautiful experiment which I've done here, but I just want to tell you that what happens in fact that you can, by optical pumping techniques, prepare this ion into a state which has, in the de-excited state of the core, which has an electric quadrupole moment, which can have one distribution of electric charge or the other, and have this quadrupole interacting with the Rydberg electron, which is a kind of probe, kind of satellite, like you can see this as an Earth satellite, which is getting some information about what's happening at the surface of the Earth. With that, they were able to measure this quadrupole moment of the strontium core, and you can use the strontium core to manipulate the outer electron and to get information, optical information about the state in which the outer electron is. So the method is quite similar to the blockade method, but then there is no blockade. It's just the Coulomb interaction between the two electrons. So it goes very rapidly because I know that I have to stop. And I will just conclude. So you see that depending upon which state, for example, the circular electron is, 54 or 52, you get a different spectroscopy for the ion core because this outer electron is slightly perturbing the different level of the quadrupole state. And you can use this either to use the strontium core to control the outer electron or to use the outer electron to control the state of the core. So I just go very quickly. And I just conclude by saying towards where these experiments are going. The idea is to have an ensemble of atoms prepared in a very well rearranged way. And what you can do, what they are doing now, is to, instead of having a bottle beam trap, you can use the core of the strontium atom to hold by the regular tweezer the strontium atom. So for the strontium atoms, you can use, and they have shown it works, you can use a Gaussian beam to trap the atom, and it does not affect the circular state. And the idea is to have a lot of atoms doing that, to go to very low temperature to eliminate black body radiation effects. And you can even, if you do the experiment between two plates, suppress spontaneous emission and have, in principle, eternal Rydberg atoms interacting over a very long time. So just to conclude, I guess I have tried to show you that circular Bohr atoms have gone a long way since they appeared in atomic physics in 1913. From ideal concepts, they have become experimental objects to manipulate and observe, to be observed individually, and their coupling to photons between each other can be controlled. And they play now an essential role in many body systems. And whether such a computer operating with Rydberg atoms or other kind of qubits will be effective as a quantum computer is still an open question, but many, many other interesting things can be done in between. Thank you very much, and I apologize for having been too long.